Hello, future engineers. Welcome to my YouTube channel. If you like my videos, please don't forget to share them to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. Here we go. This is an application of the three-moment equations. Analyze the continuous beam shown below. Also construct the shear moment diagrams and sketch the elastic curve. E is constant because the moment of inertia of each segment of the beam is different for each segment. So first we transform A into, because we have fixed ends A and D, into internal pin. Then extend it with negligible span, call that A prime. Same is true at D, so extend D prime. So we first apply three moment equations on spans A prime, AB, where moment at A prime is 0. And let's have that step. So call this x1, call that x, so that uh, w as to x equals 50 as to 4. So 50 over 4 is 12.5, therefore the height of the strip is 12.5x. So therefore the differential force is 12.5x dx. So moment, this distance therefore, because this is 7, is 7 minus x, although the span is 9. So moment at A prime is 0 plus 2 times MA, quantity 9 over 1, 9 over I, so 9 over 1, or 0 first, 2 times MA, quantity 0, A prime A, negligible span, plus 9 times 9 over 1, then plus MB times 9 over 1. Then the value of 6A1A over I1L1 for span A prime A is 0, there's no load, while the value of 6 area 2B over I2L2 for span AB is, we have integral of 12.5x dx, B is 7 minus x over L, 9, then moment of inertia 1, quantity 9 square minus 7 minus x quantity square, from 0 to 4, the variation of x 0 to 4. So 12.5x dx, 7 minus x over 9 times 1, 9 square minus 7 minus x square. Then because the horizontal line reference at A crosses A prime and B, there are no settlements, so equals 0. The value of this integral is, using your calculator, 25760 over 9. Simplifying, 18MA plus 9MB equals negative 25760 over 9. Call that equation 1. We then apply three-moment equation on spans ABC. So moment A times 9 over 1 plus 2 times MB, quantity 9 over 1, plus 10 over 2. The span BC is 10, then moment inertia 2. So 2 times MB, quantity 9 over 1 plus 10 over 2, plus MC times 10 over 2. Then the value of 6 area 1A over I1L1 is integral of 12.5x dx. This time A is 2 plus x all over L, 9, moment of inertia 1, quantity 9 squared minus quantity 2 plus x quantity squared. Integral 0 to 4, 12.5x dx, 2 plus x over 9 times 1, quantity 9 squared minus quantity 2 plus x squared. While the value of 6 area 2b over I2L2, so let's have a strip first and call that x from the left. So imagine this is W minus 20 as to x equals 60 minus 20 is 40 as to 5. Since 40 over 5 is 8, the height of the strip therefore is 8x plus 20. So after similar triangles, show that it is 8x plus 20. Therefore, the value of 6 area 2b over I to L2 is integral of quantity 8x plus 20 dx, that's dp. B is x plus 4 all over L, which is 10, moment of inertia 2, so 10 times 2. Quantity 10 square minus quantity x plus 4 square. So 10 square minus quantity x plus 4 square, limits of x 0 to 5. 0 to 5. Again, differential P. dx is distance of centroid of strip from C, which is x plus 4 all over L 10, moment of inertia 2, quantity L square minus B square. So B is x plus 4 square. Then because the reference horizontal line through B crosses A and C, so the right side is 0. So the value of this integral is 26440 over 9. This integral is 38645 over 12. So simplifying, 9ma plus 28mb plus 5m sub c equals negative 221695 over 36. Call that equation 2. Then, three-moment equation on spans BCD. So we have mb times 10 over 2 plus 2 times mc, quantity 10 over 2 plus 8 over 1.5, then plus md times 8 over 1.5. Then this time the value of 6 area 1a over I1 L1 for span BC is integral of quantity 8x plus 20 dx. Then a is 1 plus, this is, if this is x, this is 6 minus x, so 0 to 5 limits, all over L 10, moment of inertia 2, quantity 10 square minus 1 minus 6 minus x, quantity square. So plus integral 0 to 5 of 8x plus 20 dx, 6 minus x over 10 times 2, quantity 10 square minus quantity 6 minus x square. While the value of 6 area 2b over I to L2 for span CD, it consists of this concentrated load 40 times 6 all over 8 times 1.5, quantity 8 square minus 6 square. For this uniform loading, dp is 30 dx. Then let's call this distance of strip from D as x. Integral 0 to 4, 30 dx over times x. B is x because we call this distance x from the right, from D, all over L, which is 8, then moment of inertia 1.5, quantity L square minus B square. So that is B, or x. Then equals 0 because the horizontal line through C crosses both B and D. So the value of this integral is 31255 over 12. This one is 560. This integral is 1120. So simplifying, 5mb plus 62 over 3 m sub c plus 16 over 3 md equals negative 51415 over 12. Call that equation 3. Then lastly, for spans CDD prime, so we have m sub c times 8 over 1.5 plus 2 times md, quantity 8 over 1.5 plus 0, span dd prime is negligible, plus moment at d prime, which is 0, plus 6 a1a over I1 L1 for span CD is PA, so 40 times 2 all over 8 times 1.5, quantity 8 square minus 2 square. And for this integral, B is 8 minus x, so integral of 30 dx quantity 8 minus x all over 8 1.5 quantity 8 squared minus quantity 8 minus x squared. Then the value of 6 area 2b over I2L2 for span dd prime is 0. There's no load. Then equals 0. Because the horizontal line through D crosses C and D prime. They are at the same level. Simplifying, or the value of this is 400 for this integral 1440. So simplifying 16 over 3 m sub c plus 32 over 3 md equals negative 1840. Call this equation 4. So if your calculator is capable of solving 4 simultaneous linear equations, then do it for Canon calculators. But for my calculator, it is only up to 3 simultaneous linear equations. So I'll express moment at D in terms of moment at C. So moment at D is negative 0.5 of mc minus 172.5. I then substitute this md into equation 3. So 5 mb plus 62 over 3 m sub c plus 16 thirds of quantity negative 0.5 mc minus 172.5 equals negative 51415 over 12. So 5 mb, simplifying 5 mb, 62 over 3 minus 16 thirds times 0.5 of mc, it becomes 18 mc. Then negative 51415 over 12 plus 16 times negative 1 plus 16 times 172.5 over 3, it becomes positive to the right. So the net value is negative 4375 over 12. Call that equation 3. So solving equations 1, 2, and 3a rather, equation 3a. So solving equations 1, 2, and 3a simultaneously, we get MA equals negative 73.253 kilonewton meter, MB equals negative 171.519 kilonewtons meter, MC equals negative 139.277 kilonewton meter, and MD, which is negative zero point 0.5 of MC, negative 139.277 minus 172.5. So MD is equal to negative 102.862 kilonewton meter. So we bring this on the next slide. We run out of space here. Then solve for the reactions and shears at various sections. So this is the beam and the moment reactions. So let's have now the reactions applied and the reaction and the moment, internal moments. These were the results, negative, so that would be the directions. This will be the directions of the moments. So RA, RB, R sub C, and RD. So for span AB, we sum up moments about B equals 0 so that we can solve RA. So RA is, let's prepare the shear force diagram and the bending moment diagram in kilonewton meter. And RA times 9 plus 171.519 equals 73.253. Then plus the moment of the load with respect to B is 1/2 or 0.5 of 4 times 50. This is 4 thirds plus 3. So the moment arm is 4 thirds plus 3. So plus 0.5 of 450 quantity 4 thirds plus 3. So solving for RA is 37.230 kilonewtons. So imagine that shear B left is downward positive. So it is just upward minus downward forces considering AB. So shear at B just to the left is RA 37.23 minus this area of load 0.5 of 4 times 50. So shear at B just to the left is negative 62.770. For shear at B just to the right, let's consider BC. We sum up moment about C equals 0. So upward shear at B just to the right, upward positive, times 10, then plus 139.277 equals 171.519 plus the moment of the 20 uniform load. Let's divide this into rectangular and triangular load. So 20 times 5, 2.5 plus 4 is 6.5. So plus 20 times 5 times 6.5. While the moment of the triangular load is 1 half or zero point 0.5 of 5 times 40, where 40 is 60 minus 20. The moment arm is 2/3 of 5, 10/3 plus 4. So 0.5 of 5 times 40, quantity 10/3 plus 4. So solving for shear at B just to the right, it is equal to 141.558 kilonewtons. Therefore, reaction at B is 141.558 plus 62.77. Don't mind the sign. You just add. So R sub B is 204.328 kilonewtons. Then for shear at C just to the left, let's consider BC. It is downward positive, so it is shear at B just to the right. So again, shear at C just to the left is shear at B just to the right. So 1 equals 141.558 minus the area of this trapezoidal loading. So minus zero point 0.5 of quantity 60 plus 20 times 5. So shear at C just to the left is negative 58.442 kilonewtons. Then for shear at C just to the right, upward positive, we consider CD, summation moments about D equals 0. So shear at C just to the right times 8 plus 102.862, then equals 139.277 plus the moment of the 40 kilonewton load, 40 times 6, plus the moment of the 30 kilonewton per meter uniform load, 30 times 4 times 2. So shear at C just to the right is equal to 64.552. R sub C is 64.552 plus 58.442, or 64.552 minus negative of 58.442. So just add, get the absolute value, 122.994 kilonewtons. Finally, R sub D, summation moment C equals 0. So R sub D times 8, then plus 139.277 equals 102.862 plus 40 times 2 moment of the concentrated load plus 30 times 4 times 6 moment of the 30 kilonewton per meter load. So R sub D is equal to 95.448 kilonewtons. So the shear at D is negative of shear at D just to the left is negative 95.448. So it will be shown later. So first we have RA upward, which is 37.23. So let's have 75 for the shear per this graduation, and for moment by 50s. So 37.23 RA, RB is 204.328, R sub C 122.994, RD is 95.448. So from shear force diagram, we rise 37.23, then constant up to this part, and minus the area of this loading, 37.23 minus 0 0.5 times 4 times 50, negative increasing. So the ordinate here becomes negative 62.77, then constant. So check that the shear at B just to the left is negative 62.77 kilonewtons. Then negative 62.770 plus 204.328, it rises to shear at B just to the right, which is 141.558. It checks. Then constant, and minus the area of this trapezoidal loading, and it is negative decreasing. So the curve looks like that, second degree. So 141.558 minus 1 half or zero point 0.5 of quantity 60 plus 20 times 5. So the ordinate here would be negative 58.442. Then constant, that's the shear at C just to the left is negative 58.442. It checks here. Negative 58.442 plus 122.994. So it rises to 64.552, which is the shear at C just to the right. 64.552, it checks. Then constant, minus 40, so it is 24.552. And constant, minus 30 times 4. So the ordinate here is negative 95.448, which is the shear at D just to the left. So plus RD, so it loses to 0. So for the bending moment diagram, we have negative 73.253, go down. Then negative 73.253 plus the area here, which is 37.23 times 2. So it rises straight line 1.207. Then plus the area of this parabola. So let's call this x1. And let's project upward. That is x1. Remember, load, intensity of this load as to x1 equals 50 as to 4. Because 50 over 4 is 12.5. The height is 12.5 x1. Therefore, the shear in portion AB, which begins here, is 37.23 minus the area of this triangle, which is 1 half of x1 times 12.x1. So shear in AB is 37.23 minus 1 half or 0.5 of x1 times 12.5 of x1. We want to find x1 where shear is 0 here. So equate to 0. So x1 would be 2.4407 meters. Therefore, if I call this area 1 and this one area 2, area 1 would be the integral under area under the shear curve. So it is integral of the shear equation, 37.23 minus 6.25 x1 square dx1 limits from 0 to 2.4407, where 0 begins here at the 0 load. So area 1 is integral from 0 to 2.4407 of shear equation 37.23 minus 6.25 x1 squared dx1. And the value of that is 60.577 kilonewton meter. Another way of computing area 1 is 2/3 of x1, 2/3 of 2.4407 times 37.23. So I want you to check that. Then area 2, same integral except the limits from 2.4407 to 4 because x1 varies from 0 to 4. And it is equal to negative of 44.990 kilonewton meter. So 1.207 plus area 1, which is 60.577, and it is positive decreasing up to this portion. So it is equal to 61.784. So 61.784 plus area 2, which is negative 44.99, it goes down to 16.794. Then plus this area here, which is negative 62.77 times 3, so it goes straight down, and it is equal to negative 171.516. This is supposedly the moment at B, and the moment at B is negative 171.519. So there's already a very small discrepancy of 0.003 rather, which is very acceptable. Then plus negative 171.516 plus this area, which is 141.558 times 1, it rises to negative 29.958. Then we have another area to be solved, call this x sub 2. Then area 3, area 4. Then let's project upward. Let's find the value of this in terms of x2. So imagine a triangle. This is w minus 20 as 2. So this distance is 5 minus x2 equals 40 as to 5. Then 40 over 5 is 8. Therefore, the height of the intensity of this loading up to x2 is 8 times 5 minus x2 plus 20. Again, w minus 20 as to 5 minus x2 equals 40 as to 5. 40 over 5 is 8. So therefore, the intensity of this loading is 8 times 5 minus x2 plus 20. Anyway, that's given. Therefore, the shear in portion BC, beginning with this point here, 0 load, is shear at B just to the right, which is 141.558, then minus area of trapezoid, which is 0.5 or minus 1/2 or 0.5 of quantity, 60 plus 8 times 5 minus x2 plus 20 times x2. Simplifying, shear in VC is 141.558. So we have 60 plus 40 plus 20, so 120. So negative 0.5 of 120 is negative 60 times x2. Then negative 0.5 times 8 times negative x2 is positive 4x2 times x2, so x2 squared. Therefore, shear BC is 141.558 minus 60 x sub 2 plus 4 times x2 squared. Then we equate to 0 to find this x2 where shear is 0. There are two values of x2 but the other one is absorbed. So x2 is, the acceptable value of x2 is 2.9327 meters. Therefore, area 3 is integral of shear under the shear curve 141.558 minus 60x2 plus 4x2 squared dx2 from 0 to 2.9327. So area 3 is equal to 190.756 kilonewton meter. Then area 4, let's put the calculations here. From 2.9327 to 5, the limits, same shear equation, then dx2. And area 4 is expected negative. Area 4 is negative 66.300 kilonewton meter. So we then plot, we have positive decreasing. It looks like that. So let's project this 0 shear here. So negative 29.958 plus area 3, which is 190.756, positive decreasing, would be negative 29.958 plus 190.756. That's 160.798. Then plus area 4, which is negative 66.3, goes down to 94.498. Then plus this area, which is negative, so 94.498 plus negative 58.442 times 4 goes straight down. And the value here is negative 139.27, which is supposedly the moment at C. The moment at C is negative 139.277. This is negative 139.270, so there's a very small discrepancy of 0.007. And that's practically the same. Then negative 139.27 plus 64.552 times 2 goes straight up. So the value here is negative 10.166 plus the area here, which is 24.552 times 2, goes straight also. So that would be 38.938. Then we will call this x3. Then shear in this portion is 24.552 minus 30 times x3 equals 0. Therefore, x3 is 24.552 divided by 30, and I'll put x3 here. x3 is 0.8184 meters. So therefore, we have positive decreasing curve. Let's project downward. So 38.938 plus the area here of this small triangle, which is 1/2 of x3, 1/2 of 0.8184 times 24.552. It will give us 38.938 plus 1/2 of 0.8184 times 24.552, 48.985. Then plus the area of this triangle, so 48.985 plus the area of this triangle, which is negative 1/2 of quantity 4 minus 0.8184 times negative 95.448. So it goes negative, increasing down to negative 102.854, which is supposedly the moment at D, which is negative 102.862. So there's a discrepancy of about 0.008, which is expected because of rounding of values. So therefore, it closes zero moment there. So this is the moment diagram. Let's have the points of inflection, 0 moments projected upward, where concavity changes direction at these points, here, here, and here. So concave down, horizontal tangent, concave up, concave down, concave up in this portion, positive movement, concave down, then concave up, concave down. So the elastic curve would look like that. It doesn't matter on this portion, it's below. It doesn't matter as long as the concavity is correct for positive and negative bending. So that's it for this problem. This is a quite challenging problem because of the loading and because of the construction of shear moment diagrams. So I hope you were able to follow the explanation and the construction.